Let's start with some basic facts that may or may not be obvious and may even contradict what you think you know. Light moves in a straight line. At least this is true within the boundaries of our scenario. Huge masses may bend light, or boundaries between media might refract it. But these effects play no role when light travels from Sun to Earth and through the atmosphere near noontime, far from sunset or sunrise. To see an object, light from that object must hit the observer's eye. Light traveling in other directions may hit objects and illuminate them, making them visible when the reflected light in turn reaches the eye. The Sun emits light on every point of its surface in every direction. This may be a surprising fact, as you may have learned that sunlight reaching the Earth is always parallel. But this is just a consequence of the light not hitting Earth not being taken into account, and the light that reaches Earth being parallel simply due to the great distance between Sun and Earth and applied trigonometry. Now what immediately follows is that the light that makes the Sun visible is the light within a cone from the Sun to the eye of the observer, marked in yellow here. The angle of opening of the cone is identical to the apparent size of the Sun of about half a degree or 31-32 arcseconds. To hide the Sun from an observer, anything that has the same angular size as the Sun or is larger suffices. That might be a coin held near to the observer, or, well, the Moon, of course. The coin will not give you the same effects as a total eclipse. That is because the coin is held within the atmosphere, well after the atmosphere has scattered parts of the light that now will reach the eye of the observer from different directions. Both the Earth's orbit around the Sun and the Moon's orbit around Earth are not exactly circular. That means that an eclipse can occur when both the Sun and the Moon are nearer or farther away and therefore vary their relative size. In cases where the Sun is nearer and or the Moon is farther away, you'll get a partial eclipse, or if you're lucky, an annular eclipse. A second observer, some distance away, will see the Moon slightly offset and therefore not covering the Sun completely. For him, the eclipse will only be partial, unless of course the apparent size of the Moon is sufficient to still block the complete sunlight at his position. So, why is the width of the area of totality smaller than the Moon's diameter? Simple. Because the sunlight being blocked forms a cone. A cone that would have its peak somewhere beneath the Earth's surface, but that has still a smaller diameter on the ground than where the Moon blocks the Sun in reality.